What happens when you ask an AI to calculate something, and it actually does the math instead of just talking about it? You'll see how to assemble a complete calculator agent from scratch, where the model doesn't just describe arithmetic. It performs it by calling tools, handling results, and looping until the job is done. The pattern ties together state management, tool execution, and decision logic into a single workflow that runs start to finish.
Step 1. Define tools and model. From LangChain, tools import tool. From LangChain, chat models import init chat model. Model equals init chat model. Claude Sonnet 45202, 50929. Temperature equals 0. Define tools. At tool. Def multiply a int b, int. Multiply a and b. Args. A, first int. B, second int. Return a asterisk b. At tool. Def add a int b, int. Adds o and b. Args. A, first int. B, second int. Return a plus b. At tool. Def divide a int b, int float. Divide o and b. Args. A, first int. B, second int. Return a slash b. Augment the LLM with tools. Tools equals add, multiply, divide. Tools by name equals tool name. Tool for tool and tools. Model with tools equals model. Bind tools, tools. Step 2. Define state. From LangChain, messages import any message. From typing extensions, import type dict, annotated. Import operator. Class messages state, type dict. Messages, annotated list any message, operator add. LLM calls, int. Step 3. Define model node. From LangChain, messages import system message. Def LLM call state, dict. LLM decides whether to call a tool or not. Return. Messages. Model with tools invoke. System message. Content equals, you are a helpful assistant tasked with performing arithmetic on a set of inputs. Plus state messages. LLM calls. State, get LLM calls 0 plus 1. Step 4. Define tool node. From LangChain, messages import tool message. Def tool node state, dict. It performs the tool call. Result equals. For tool call in state messages -1, tool calls. Tool equals tools by name tool call name. Observation equals tool. Invoke tool call args. Result, append tool message. Content equals observation. Tool call ID equals tool call ID. Return messages. Result. Step 5. Define logic to determine whether to end. From typing, import literal. From Langgraph, graph import Stategraph start end. Conditional edge function to route to the tool node or end, based upon whether the LLM made a tool call. Def should continue state. Messages state literal tool node, end. Decide if we should continue the loop or stop, based upon whether the LLM made a tool call. Messages equals state messages. Last message equals messages -1. If the LLM makes a tool call, then perform an action. If last message tool calls, return tool node. Otherwise, we stop, reply to the user. Return it. Step 6. Build agent. Build workflow. Agent builder equals Stategraph. Messages state. Add nodes. Agent builder, add node. LLM call, LLM call. Agent builder, add node. Tool node, tool node. Add edges to connect nodes. Agent builder, add edge start, LLM call. Agent builder add conditional edges. LLM call. Should continue. Tool node end. Agent builder add edge tool node. LLM call. Hash compile the agent. Agent equals agent builder compile. From IPython, display import image display. Hash show the agent. Display image agent, get graph x-ray equals true. Draw mermaid PNG. Hash invoke. From LangChain, messages import human message. Messages equals human message. Content equals add 3 and 4. Messages equals agent invoke. Messages. For M in messages. M pretty print.
This demonstrates the stateful workflow pattern for building AI agents, where the system maintains context across multiple steps while delegating decisions to specialized components. The core concept is a directed graph where nodes represent either reasoning steps, the LLM, or action steps, tools, connected by conditional edges that determine flow based on runtime state. What makes this distinctive is the separation of control logic from execution logic, allowing complex behaviors to emerge from simple, composable parts. The pattern works through declarative state management and conditional routing. The agent's state persists between steps, with each node transforming it in a predictable way, while edges use state inspection to determine next actions. This creates a loop where the LLM reasons about tool use, tools execute and return observations, and the cycle repeats until a terminal condition is met. The power comes from treating the LLM as just another node in the graph, subject to the same routing rules as tool nodes, which enforces consistency in how state flows through the system. This approach solves the problem of orchestrating multi-step, tool-using agents without hard-coding sequences, or overloading the LLM with control logic. It's particularly valuable for tasks requiring iterative refinement, like calculations, research, or multi-tool workflows, where the path isn't known in advance. The trade-off is added complexity in graph definition, but the payoff is flexibility. You can modify behaviors by adjusting edges or nodes without rewriting core logic, and the visual graph representation makes debugging intuitive. Let's break it down. From LangChain, tools import tool. Imports LangChains at tool decorator for creating AI callable functions. This transforms regular Python functions into tools that the LLM can invoke, with type hints and docstrings defining the tool's interface. Model equals init chat model. Claude Sonnet 45202, 50929. Initializes a chat model using LangChain's init chat model with model ID, Claude Sonnet 45202500929, and sets temperature equals 0 for deterministic outputs. Note this differs from the standard AWS Bedrock initialization pattern shown in docs, which uses provider-specific IDs like Anthropic. Claude 3-5 Sonnet 20,240,620 v1, 0 with explicit model provider parameter. At tool, def multiply a int b, int, multiply r and b, args, a first int, b second int, return a asterisk b. At tool, def add a int b, int, adds o and b, args, a first int, b second int. These are LangChain tool definitions using the @tool decorator. Each function becomes an AI callable operation with type hints defining the schema and docstrings, providing natural language descriptions. The pattern creates a clean interface between Python logic and language model interactions. @tool, def divide a int b, int float,
divide O and B. Args. A, first int. B, second int. Return a /b.
Tool definition for AI callable division operation. The @tool decorator exposes this function to the language model, with type hints and docstring defining the tool's schema. Returns a float to handle fractional results from integer division.
Hash augment the LLM with tools. Tools equals add, multiply, divide. Tools by name equals tool name, tool for tool and tools.
This creates a tool registry for the LLM. The list tools collects all callable functions, while tools by name builds a lookup dictionary mapping tool names to their implementations, critical for efficient tool dispatch when the LLM requests specific operations. This pattern enables dynamic tool selection at runtime.
Model with tools equals model. Bind tools, tools.
This binds the arithmetic tools to the language model, creating an AI that can invoke them. The bind tools method attaches the tool schemas to the model's context, enabling tool selection and argument extraction during inference. Without this, the model would lack awareness of available tools.
From LangChain, messages import any message. From typing extensions, import type dict, annotated. Import operator.
This code defines a messages state typed dict where messages uses Langgraph's built-in add messages reducer, imported here as operator add for convenience, to automatically handle message list updates, converting shorthand formats, like OpenAI-style dicts, to proper message objects and managing list concatenation during state transitions, while LLM calls tracks invocation count as a simple integer. The reducer ensures new messages are properly appended to the existing list when nodes return message updates.
Class messages state, type dict. Messages, annotated list any message, operator add. LLM calls, int.
This messages state uses operator add for basic list concatenation of any message objects, simply appending new messages to the existing list. Unlike Langgraph's recommended add messages reducer, which handles OpenAI format shorthand and message updates, this implementation keeps it minimal with direct list merging via plus operations. The LLM calls counter tracks LLM invocations separately from message state.
From LangChain, messages import system message.
Imports system message from LangChain, a specialized message type for system-level instructions to the LLM. This sets the AI's behavior and context before processing user input, ensuring consistent responses aligned with the defined role.
Def LLM call state, dict. LLM decides whether to call a tool or not. Return. Messages.
This node invokes the LLM with the current message history and bound tools, returning the model's response, which may contain tool calls, while incrementing the LLM calls counter in the state. It doesn't make routing decisions. It simply passes the input state to the model and updates the state with the raw output.
From LangChain, messages import tool message.
Imports tool message from LangChain. The message type used to return tool execution results to the LLM. This enables the agent to communicate back the outputs of function calls in a structured format the model understands.
Def tool node state, dict. It performs the tool call. Result equals. For tool call in state messages -1, tool calls. Tool equals tools by name tool call name. Observation equals tool. Invoke tool call args. Result, append tool message. Content equals observation. Tool call ID equals tool call ID.
This is the tool execution handler. It processes each tool call from the LLM's last message, invokes the corresponding tool function, and packages the results as tool message objects for the next cycle. The pattern ensures tool outputs re-enter the conversation flow with proper tool call IDs for tracking.
Return messages. Result.
This returns the tool execution results wrapped in the state format. The messages key contains tool message, objects that the LLM will process in the next cycle, maintaining the conversation flow.
From typing, import literal. From Langgraph, graph import Stategraph start end.
Imports literal for type-safe string literals and Stategraph for defining workflows. These are core components for building the agent's decision graph, where start and end mark entry and exit points.
Def should continue state. Messages state literal tool node. End. Decide if we should continue the loop or stop, based upon whether the LLM made a tool call. Messages equals state messages. Last message equals messages -1.
This routing function determines the next step in the agent's workflow. It examines the last message to check for tool calls, deciding whether to continue processing or end the chain. This is the conditional edge logic that enables the loop between LLM calls and tool execution.
Hash build workflow. Agent builder equals state graph. Messages state.
Initializes the workflow using LangChain's Stategraph. This creates the foundation for our agent's execution graph, defining how nodes will connect and interact while maintaining the shared state we defined earlier.
Agent builder, add node. LLM call, LLM call. Agent builder, add node. Tool node, tool node.
Registers the two core processing nodes in the workflow graph. The LLM call node handles AI decision-making and tool invocation requests, while tool node executes the actual tool operations. This separation enforces clean responsibility boundaries between planning and execution.
Agent equals agent builder compile.
This compiles the state graph into an executable agent workflow. The compile method transforms the node definitions and edges into a runnable state machine, handling the orchestration between LLM calls and tool execution automatically. Without this step, the graph remains just a blueprint compilation, makes it operational.
From IPython, display import image display.
Imports image and display from IPython's display utilities. These enable rendering the agent's workflow graph directly in Jupyter notebooks, providing visual debugging of the state machine's execution flow.
Hash show the agent. Display image agent, get graph X-ray equals true. Draw mermaid PNG.
This visualizes the agent's execution flow as a directed graph. The X-ray equals true parameter exposes internal state transitions, while draw mermaid PNG generates a diagram showing how nodes, LLM calls, tool execution connect and loop, critical for debugging complex workflows.
From LangChain, messages import human message.
Imports human message from LangChain, the message type for user inputs in chat workflows. This enables creating human-originated messages that the agent will process, distinguishing them from system or tool messages.
Messages equals human message. Content equals add 3 and 4.
Initializes the conversation with a user request. This human message creates the first input to the agent, triggering the workflow with the instruction add 3 and 4, the starting point for the agent's decision-making and tool execution.
Messages equals agent invoke. Messages.
This invokes the compiled agent graph with the initial user message. The agent processes the input through the LLM and tool nodes as defined in the workflow, returning the final response with all intermediate messages.
For M in messages, M pretty print.
Iterates through the agent's response messages and prints each in a human-readable format. The pretty print method handles complex message structures, including tool calls and results, making debugging and output inspection straightforward. Langgraph agent construction pattern. This implementation demonstrates the core workflow of building stateful, tool-using agents where the LLM dynamically routes between tool execution and response generation. The conditional edge logic in should continue must handle both tool calls and final responses, as missing either case will break the execution flow. State management through messages state and Stategraph creates a clean separation between message history and tool operations, making the agent's behavior predictable and debuggable.
The LLM call that summons the tool node is itself summoned by the tool's return.